In 1905, a young Albert Einstein revolutionized our understanding of space and time with his special theory of relativity. He showed that time wasn't a constant, but instead it was relative to the observer's motion. This groundbreaking theory met with both excitement and skepticism. Many physicists struggled to accept its radical implications, yet Einstein was not satisfied. He knew his theory was incomplete. Einstein's special relativity worked beautifully for objects moving at constant speeds. However, it didn't explain the force of gravity or the motion of accelerating objects. Einstein felt a deep sense of unease. He believed a truly elegant theory should encompass all aspects of the universe, including gravity. He embarked on a quest to find a more comprehensive theory. This quest would consume the next decade of his life. Einstein, with his relentless curiosity, questioned the very nature of gravity. He sought a theory that could explain why objects fall to the Earth. He wanted to understand why planets orbit stars. His journey would lead him to challenge centuries of established physics. He would ultimately reshape our understanding of the cosmos. Newton's law of universal gravitation had served well for centuries. It accurately described the force of attraction between objects with mass. However, it didn't explain how gravity worked over vast distances. The concept of action at a distance puzzled Einstein. He refused to believe that gravity could act instantaneously across the universe. Einstein's dissatisfaction with existing explanations fueled his determination. He imagined a universe where the laws of physics remained consistent for everyone. This meant finding a way to incorporate gravity into his framework of relativity. He knew that acceleration and gravity were somehow deeply connected. His intuition told him that there had to be a deeper connection between gravity and motion. Einstein envisioned a universe where gravity wasn't just a force but a manifestation of something more fundamental. This relentless pursuit of a unified theory would lead him down a path paved with thought experiments. These thought experiments would challenge the very foundations of physics. One of Einstein's most famous thought experiments involved a simple scenario: a window washer falling from a ladder. Einstein realized that the falling window washer wouldn't feel the force of gravity. Instead, he would experience a sense of weightlessness, as if he were floating in space. This simple observation sparked a profound realization. Einstein recognized that gravity and acceleration were not distinct forces, but two sides of the same coin. He called this the equivalence principle, a cornerstone of his general theory of relativity. He argued that within a closed system, it would be impossible to distinguish between the effects of gravity and the effects of acceleration. Einstein imagined a beam of light shining across an accelerating rocket ship. He realized that the light beam would appear to bend downwards from the perspective of an observer inside the rocket. This led him to a remarkable conclusion: gravity itself must bend light. This insight would have profound implications for our understanding of the universe. Section 4. The fabric of space and time. Einstein's breakthrough lay in realizing that gravity wasn't a force acting through space but rather a property of space itself. He proposed that massive objects like stars and planets warp the fabric of space-time around them. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a dip in the sheet, distorting the fabric. Einstein envisioned space-time as a four-dimensional fabric. This fabric could be bent and curved by the presence of mass and energy. Objects moving through this warped space-time would follow curved paths. These paths, he realized, were not due to a gravitational force but rather a consequence of the curvature of space-time itself. To describe this revolutionary idea mathematically, Einstein turned to a complex branch of geometry called Riemannian geometry. This form of geometry allowed him to describe the curvature of space-time. It also allowed him to formulate his general theory of relativity. The equations he derived were elegant, yet incredibly complex. These equations predicted that gravity's influence traveled at the speed of light, not instantaneously as Newton had thought. Section 5. Bending starlight, proof in the eclipse. Einstein's general relativity made several testable predictions. One of the most remarkable was the bending of starlight around massive objects. Einstein predicted that the sun's gravity would warp the fabric of space-time around it. This warping would cause light from distant stars to bend as it passed close to the sun. In 1919, during a total solar eclipse, astronomer Arthur Eddington set out to test Einstein's prediction. Eddington traveled to the island of Principe off the coast of Africa. There he photographed the stars that were visible near the eclipsed sun. His observations confirmed that the starlight did indeed bend around the sun. The amount of bending matched Einstein's predictions precisely. News of Eddington's findings made Einstein an instant celebrity. The world was captivated by this strange new theory that challenged our fundamental understanding of the universe. General Relativity had passed its first major test. It cemented its place as one of the most important scientific theories of all time. Section 6. Black holes and time warps. The universe's extremes. General Relativity's implications extended far beyond the bending of starlight. The theory predicted the existence of black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. It also suggested that time itself is not absolute but is affected by gravity. Time slows down in stronger gravitational fields. These mind-bending concepts, once considered purely theoretical, have now been supported by numerous observations. Astronomers have discovered supermassive black holes at the centers of galaxies. They've observed the time dilation effects predicted by general relativity. These observations continue to solidify Einstein's legacy as a visionary who unlocked some of the universe's deepest secrets. The theory's impact on our understanding of the cosmos is immeasurable. It has opened up new avenues of research in astrophysics. It has provided us with tools to study the universe's most extreme environments. From the Big Bang to the evolution of galaxies, general relativity has become an indispensable tool for cosmologists. Section 7. Unifying the cosmos. The quest continues. General relativity explains the universe on a large scale, but it clashes with quantum mechanics. Physicists aim to unify these two pillars of modern physics. This quest for a unified theory is one of the most significant scientific endeavors. Einstein's legacy inspires us to explore the cosmos and seek deeper understanding.